Yeah, hello everyone. My name is Rudolf Zeitler, and this is a recording for the 2020 virtual workshop on Riemannian scalar curvature in honor of Misha Gromov. And maybe before I start, I would like to thank the organizers for putting this event together and allowing us to interact in this manner. So I'm looking forward to this very much. So my talk will be about width, largeness, and index theory, and this will be the first part of this talk. And although it's not part of the title, this talk will be about scalar curvature. And to begin, I want to mention a recent question or conjecture due to Misha Gromov, which states the following. This is the so-called bandwidth conjecture, which states that if you have a closed manifold M, and which should have a dimension not equal to 4, and you also assume that it does not admit a metric of positive scalar curvature, and then you take the cylinder over this manifold. That's what Gromov calls band in this context, or a band. And you take a Riemannian metric which has a lower scalar curvature bound, which is positive on V. And we, for convenience, rescale this to be the scalar curvature of the n sphere, which is n times n minus 1. And in this situation, so maybe that's the picture you should take into account. You have the cylinder and you have some metric on this, so it maybe doesn't look quite like a cylinder, so maybe it looks like this. And then you have the two boundary components of this compact interval here. And the statement is that the distance between these two boundary components is a priori bounded. Yeah, if you have this scalar curvature bound, then the bound is 2 pi over n. And otherwise, if you have some other scalar curvature bound here, then you get here a constant and the square root of the scalar curvature in the denominator as a bound. And if you think about this at first glance, that might look actually quite curious, because this looks more like a kind of comparison geometry that we are maybe more used from sectional curvature or maybe rigid curvature. And usually we might think that scalar curvature is not quite good enough to give us like distance estimates. But the sort of idea here is that since we start with a manifold which itself does not admit positive scalar curvature, then somehow this positivity here on the cylinder must express itself somehow in maybe, let's say, in the horizontal direction. And if it stays positive for too long, then the cylinder must collapse eventually. That's the heuristic idea, and that's kind of what's also behind this drawing. And actually, one can sort of make this a bit more quantitative. The reason of this particular constant here is that if you perhaps start with a flat metric, or it's enough to have a scalar flat metric on M, let's assume that exists, then you can write down this warped product metric here, where you just put this cosine function here. And then this precisely has this scalar curvature. And you see that it stays alive until, sort of in both directions, until pi over n. And at the boundary pi over n, it collapses here, this function. And this example shows you that you can actually almost realize this inequality here, at least if you start with a scalar flat metric here. And if you don't have that, then you can make it almost flat by rescaling it, and then you can still approximately achieve that. So this bound, that's also something that Gromov realized, this bound is the sort of best one that you can hope for in this setup. All right, and Gromov in his recent metric inequalities paper proved this essentially for all the manifolds which are accessible to the Shane-Yao minimal hypersurface methods. So for all these manifolds where you can show using the Shane-Yao minimal hypersurface method that it doesn't admit PSC, you will be able to get such an inequality. The easiest example for that is our favorite, the torus, that you could put into this conjecture, and it's true for that. And actually in the Gromov's 4 lectures, which are also posted on the workshop homepage, he suggests an even more general approach that might give that in more general setups. Today, my goal is, however, to go into a different direction. And instead of going through this minimal hypersurface method, there is another method that's also sort of very popular in getting obstructions to positive scalar curvature. That is the Dirac operator, the index theory method. So that is the goal for my talk today, is to approach this kind of conjecture from the point of view of index theory and see what index theory can say about this. And since this is supposed to be the sort of introductory part of the talk, I will spend some time now to give an overview, a sort of a high-level overview of index theory in the way that we need it. What is index theory in this context, or what do we need here? So the first thing to apply the Dirac operator index theory method is that we need to have a spin manifold. So that's sort of the major restriction of this method, that we need to assume this. Actually, we don't need to assume that M, the manifold we're working with, has is spin. It's usually enough to have some covering, which is spin, and the method can be adapted to that. But to not overload the presentation today, I will not take this into account and basically take it as a standing assumption that my manifolds are all spin. And if we have a spin manifold, then we have a nice geometric differential operator, the spinor-Dirac operator, which acts on sections of the spinor bundle. And in the basic case, the sort of interesting situation is when the dimension of the manifold, so n is the dimension, is a multiple of 4, and then this spinor bundle decomposes into 2 parts. So it's C2 graded, and the Dirac operator is also graded with respect to this grading, and that means it is odd in the sense that you only have off-diagonal terms in the Dirac operator if you split it up according to the grading. And as I put here into the notation, the operator and sort of this bundle that depends on the choice of the Riemannian metric. So that is sort of going to be part of this. And now we assume in this part that M is also closed. Then D has very nice properties. In particular, it's a self-adjoint Fredholm operator. And particularly the interdimension of the kernel of this operator is finite. Since it's self-adjoint, it doesn't have an index, but you can exploit this algebraic symmetry here to extract an index by just basically taking the index of 1/2 of the operator. Or in other words, you define the index of your operator as the dimension of the kernel of the one part minus the dimension of the kernel of the other part. And that is some integer. And now, what about this integer? So what does this have to do with the things that we are interested in the relation to scalar curvature? So there are sort of 2 facts that make this work very well in connection with scalar curvature. And the first one is maybe too simple to say, but it is sort of important. It's that the index, although the operator depends on the metric, the index does not. So the index is really just an invariant of the manifold. And in fact, the Atiyah-Singer index theorem tells us what it is. It is the A-hat genus of the manifold, which is a certain characteristic number, which can be computed by pairing the homological fundamental class of the manifold with the A-hat class of the manifold. So that's the first part. And the second part is the Schrödinger-Lichnerowicz formula, which tells us that the square of the Dirac operator, so the Dirac Laplacian, if you want, is a connection Laplacian, as usual, plus a curvature term. And the curvature term you get here is precisely the scalar curvature. And these 2 things together allow you to say something about scalar curvature using the Dirac operator. Because that is sort of the corollary of these two observations, or to these two facts, which were first used by Lignerovich in the 1960s, is that if you have a closed spin manifold and the scalar curvature is positive, then the A hat genus must vanish. And how is this proved? Well, this just follows from this formula. So if the scalar curvature is positive, then since this is a compact manifold, the scalar curvature is bounded below by some positive constant. And let's say we normalize it such that it's just sigma times n minus 1, where sigma is some positive constant. And then the square of the Dirac is given by this plus the scalar curvature. And now this can bound it below by sigma times n squared over 4, which is a positive constant. Here you might say, wait a minute, I only have sigma times n times n minus 1. Why I have n squared here? That's a sort of small improvement to this inequality, which in spin geometry is actually very important, to Thomas Friedrich, also in the 80s, which tells you that you can improve this bound a little bit and you actually get an n squared rather than an n times n minus 1 here. But for this argument, it doesn't really matter. I just put it here for later use. And it's for us here, it's just important that it's positive. And then spectral theory tells us that the kernel of this operator must be 0. And then the kernel of both parts of the operators, both parts of the operator must have 0 kernel as well. And the index is therefore just the difference of two zeros, which is 0. So, and since the index now is just the A hat genus, we get this corollary. And maybe the equivalent statement, which is probably more important, but it's of course the same, is the sort of contraposition of this, is that now if the A hat genus doesn't vanish, then this follows that there exists no metric with positive scalar curvature, because you can compute the A hat genus with any metric you choose by this property here. So if it's non-zero, then this obstructs the existence. Okay, so this is the first important connection to index theory, which started with Lignerovich. All right, now what are examples where this can actually be applied? So the, I think, simplest, lowest dimensional example is the Kummer surface, which is a 4-manifold, which has a non-vanishing A hat genus, and which for this reason does not have a metric of positive scalar curvature. Now, what about other examples? So for instance, what about the torus that I mentioned before? Well, the A hat genus of the torus is always 0. So even in those cases where this is a multiple of 4, this is always 0. So this does not show us that torus does not admit a metric of positive scalar curvature. Now, does the torus admit PSC? Well, the answer is, I think we all know this, of course. No, this is questions which was settled in the 80s by Shane and Yao and by Gromov and Lawson. However, index theory, as far as I explained, so far explained it now, is not enough to show this, because the A hat genus is just 0. So the way that Gromov and Lawson went about this, so they actually used index theory, but in a sort of slightly more sophisticated way. And what they did is that essentially in this formula here above, you can do the following. So you can twist your operator with some bundle over your manifold, then then you can twist this operator with your bundle. And if you do this, then you get an additional term here, which is a curvature term that depends on the curvature of your bundle you twist with. And in particular, if this was a flat bundle, then you could do the same kind of argument and get sort of index invariants that come from these twisted operators here. And you don't actually quite need that this is 0. It's enough that you sort of have many bundles such that these curvatures here become arbitrarily small. And if you can extract non-trivial index information out of those, then you will be able to show that your manifold does not admit the metric of positive scalar curvature. So that's kind of very roughly the extension that Gromov and Lawson used to index theory to find these obstructions. And later, this kind of way was sort of reintegrated into sort of one kind of index. And that's the next thing I want to talk about now. So there are some generalizations of the index that sort of take this kind of approach into account. And the first one that doesn't quite go into this direction, but is also important, is a slight refinement of the Dirac operator, which doesn't have an index in the integers, but an index in the real k-homology of the point, where the dimension is just the dimension of the manifold. You could also view this as the real k-theory in degree minus n, that would be the same. And that gives you sort of additional information depending on the dimension modulo 8. So in dimension which are multiples of 4. So this in this case is the k-homology is really just the integers, and this index is the old index, so it's the A-hat genus or 1/2 of the A-hat genus. But there are interestingly 2 additional non-trivial cases, that is the dimension mod congruent 1 and congruent 2 modulo 8. Here you have a C2 invariant, and this is subtle invariant. And for instance, Hitchin realized that there are actually exotic spheres in these dimensions, starting from dimension 9 and 10, which do not admit positive scalar curvature, precisely for the reason that this kind of refined index does not vanish in C mod 2. So that's the first generalization of the index. So we can go from the integers to real k-theory. And this is actually quite powerful. So first of all, Gromov and Lawson showed that if you have a simply connected manifold which does not admit positive scalar curvature, then M must be spin. And now in this situation, there is a sort of seminal result to Stefan Stolz, which says that a spin manifold of dimension at least 5, which is simply connected, admits positive scalar curvature if and only if this kind of index, which is the alpha invariant, which is denoted by the alpha invariant, is 0. So in the simply connected case, this refined index actually classifies completely the manifolds which admit positive scalar curvature. If you want to go beyond simply connected, then you need to refine your index once more. And there is, so there sort of these idea with the flat bundles in a way comes into play. So a flat bundle in a way is a representation of the fundamental group. And now the idea is that you basically want to take the universal flat bundle that exists, and that's kind of the universal representation of the fundamental group. Of course, what that should precisely mean is not clear, but because this cannot be realized by a finite dimensional bundle, usually, if the fundamental group is infinite. But if you are willing to replace your bundles by bundles with infinite dimensional fibers, where the fibers are certain C-star algebras, then you can do this. And that is leads to the so-called Rosenberg index. What you do here is you do what I suggested above, twist your operator by a bundle, and the bundle you use here is the so-called Mischenko bundle, which is as fibers has the universal group sister algebra of the fundamental group, and you take the representation of the fundamental group by left multiplication on its own sister algebra and construct the associated bundle, and that gives you a bundle over your manifold. And the sort of index theory allows you to construct an index of this operator twisted with this infinite dimensional bundle. And this now lives in the real K-theory of the group sister algebra of the fundamental group. And indeed, this index is good enough to deal with the torus. So this index of the torus is non-zero. And in general, for like both of these indices, the same principle applies as above. If the index or the sort of invariant is non-zero, then M does not admit a metric of positive scalar curvature. All right. Unfortunately, now you might ask if such an equivalence also holds for this index. If you have a fundamental group, that's not the case. So Thomas Schick constructed a counterexample to this question. There exists indeed high-dimensional spin manifolds which do not admit positive scalar curvature, but the Rosenberg index is 0. So here, in the case where you have a fundamental group, the situation is a little bit more subtle. You cannot just classify this situation via this kind of index. But nevertheless, this is very useful. And to explain this, I want to give a slightly different point of view to this as well. So there is a connection to the sort of Novikov and Baum-Kohn conjectures, which sort of was first elucidated by Rosenberg. So if you have your manifold, then you have a classifying map into the classifying space of the fundamental group. And then you can map from the K-homology of your manifold into the K-homology of the classifying space. And there is an analytic assembly map, which I would denote here by, or I would call the Novikov assembly map, which maps the K-homology of the classifying space to the K-theory of the group sister algebra. In case that pi1 is torsion-free, this is actually the same as the Baum-Kohn assembly map. In general, it's something related, but a little bit more special. And the relation to this, what I discussed above, is that if you take the K-homological fundamental class of your manifold and you map it through here, then you precisely get the Rosenberg index. And the good thing about this is that in many cases, we actually know that this map here is injective or rationally injective. So to check non-vanishing of this, we only need to check if the thing doesn't vanish here. So this is what the sort of rational strong Novikov conjecture states, that this map here, this nu, the Rosenberg, the Novikov assembly map, is injective rationally. And this indeed holds for many, many groups. So for instance, if M is non-positively curved, this was something which was first proved by Kasparov. And another maybe large class of groups is all those groups which causally embed into Hilbert space, which is a result of Tugulian U. Much more can be said about this, but I will leave it at that, not in order to not turn this into a survey on the Novikov conjecture. But maybe this is a little bit too abstract, and one wants to understand this just in terms of ordinary homology, and this can be done. So there is the Pontryagin character, which is just a real version of the Chern character, which is, for instance, on K-homology, looks like this. So it maps K-homology into homology. And in case you plug in the K-homological fundamental class of a manifold, you just get the cap product of the homological fundamental class with the total A hat class of your manifold. So this tells you that sort of this guy here, you can again compute it in terms of characteristic classes. And of course, that's how the Pontryagin character is defined after all. But for us, what this means is that you can reformulate the rational non-vanishing of this Rosenberg index in case that the Strong-Novikov conjecture for your group holds. In this case, so if that holds, then the rational non-vanishing of this index we are interested in, after all, is equivalent to the non-vanishing of these kind of characteristic numbers here, where we take some cohomology class of the classifying space, and you look at these so-called higher A hat generas, and if one of them is not zero, then this tells you that rationally this guy doesn't vanish here, basically by this formula here, and if this is rationally injective, then if you map it once further, it will still be non-zero. So this tells you precisely this, that this kind of maybe somewhat mysterious object here, it's non-vanishing in good cases, can actually be formulated just in terms of these so-called higher A hat generas. All right. And in particular, what this means is that if M is spherical and the group satisfies the Strong-Novikov conjecture, then you can just take as your cohomology class here, take the class that is dual to the homology class in top degree. If M is spherical, then M is just can be taken to be pi 1. So since the total A hat class in degree 0 is also just 1, you can reinterpret this as a sort of trivial kind of higher A hat genus, and it's non-zero. So by the Strong-Novikov conjecture, the Rosenberg index doesn't vanish, and therefore M does not admit positive scalar curvature. All right, and now sort of my little survey on index theory is complete, and I want to connect this back to the conjecture on bandwidths. So that's the sort of main result is that the index theory says something about the bandwidth conjecture. So the result is that there exists some constant c, and it actually is, now we know it has to be 2 pi, or it can be 2 pi, such that if you have a closed spin manifold of non-vanishing Rosenberg index, so this is this Rosenberg index I talked about now, then every Riemannian metric on the band satisfies this a priori bandwidth estimate in case that the scalar curvature is bounded by n times n minus 1. And when I proved this last year, I obtained a constant that was slightly below 20. And recently, a couple of months ago, Simone Cecchini actually greatly improved this and showed that this method, and I can actually give C a constant equal to 2 pi, which is, as discussed earlier, the optimal constant that one can hope for. So indeed, index theory can also prove these questions. So whenever you have a manifold that does not admit positive scalar curvature because of the Rosenberg index, then you get the bandwidth estimates conjecture with the optimal constant after this result to Cecchini. And maybe as sort of two consequences, the bandwidth conjecture for this reason always holds if M is simply connected. For this, you just combine the results of Gromov and Lawson and Stolz that I mentioned before, because if it's simply connected and does not admit PSC, then it must be spin, and then by Gromov and Lawson, and by Stolz, it must have non-trivial alpha invariant, and then you can apply the theorem and you get that the conjecture holds. And also, if M is spherical and pi1M satisfies the strong Novikov conjecture, then we also know by what I explained before that the Rosenberg index is non-zero, and therefore the conjecture holds to the theorem. All right, this will be the end of the first talk, and it was suggested that after the first talk, it would be helpful to have some background reading material. I just made an arbitrary selection of some relevant papers that serve as a sort of background for what I talked about now. So for the conjecture, this can be found, and the context of this is explained in the recent metric inequalities of scalar curvature paper of Gromov. Then a lot about index theory and positive scalar curvature and the Dirac operator. Actually, the sort of foundational work on this, in a way, is the sort of 1983 paper of Gromov and Lawson. And the sort of addendum to this, due to Rosenberg, where sort of this is reinterpreted in terms of C-star algebras and the Novikov conjecture. And sort of these are the sort of relevant basic research papers that started this field and these questions that I've talked about. And maybe as a selection, there are also two surveys, one by Rosenberg and Stolz, and another one by Schick, which also explain many of these ideas. So then thank you for listening so far, and see you in the second part.